Challenge vehicle. Tell me about your vehicle, who you are, and why you're here, please.
My name is Bob Bittner. I'm the test lead on the project, and this is Carnegie Mellon's 2007 Chevy Tahoe named Boss. It works off of radar, GPS, and lasers. Makes smart decisions about the world around it, and makes its way down the road to where it needs to get to.
Okay, how did you do in the Urban Challenge?
We were the victors.
Excellent. By how much of a margin?
It was a 20-minute margin.
Very good. Great. And when was that? 2007?
That was November 3rd, 2007.
And what else will you use this vehicle for in the future?
The initial application was from DARPA, the Defense Advanced Research Projects Agency. They'd like to see pull people out of the convoys, especially overseas, to keep them safe. Here, though, what you see is a lot of the subsets of the technology pulled out and introduced into the vehicles that we're driving every day. You'll end up with a lot of early warning for accidents, be able to monitor the world around it, what's going on, be able to tell us about lane departure and accident avoidance, obstacle avoidance, defensive driving.
That's starting to get into cars right now these days, on high-end cars a little bit. We've seen a little bit of some of those items.
Right. And I think that's the way it'll be introduced into society so that they can accept it. Right now, I don't think people are ready to see a car just driving itself down the road.
Okay. Some statistics on this. How much did it cost? How long did it take to build? How much does it weigh? Performance, speeds?
We didn't really add that much weight to it. I believe the gross weight is around 6,000 pounds.
Weight enough to start with.
It works very, very well. Obviously, it works very well.
Yes.
The project itself, from when we received the vehicle, was 14 months until the race. So it was a very tight timeline, and that's one of the reasons that we have the sensors on the vehicle the way it is. What we did was we put a common platform on the top, and we ran through a lot of sensors to see which ones worked, which ones didn't, and so we didn't spend a lot of time integrating them flush into the vehicle. We just figured out what it was that worked and made ourselves as ready for the race as we could be.
Okay, how many people worked on it?
We had a core team out of Carnegie Mellon, their target racing team. We also had embedded engineers from General Motors, Caterpillar, Continental, and Intel.
How many students worked on it?
Off the top of my head, I really don't know. There were a lot of students involved. Same with faculty and staff.
How many of them got C- on the project?
Probably not too many.
They're all bright kids, I imagine. Very good. And what performance can you get out of it in terms of top speed, where it's capable of running, or average speed, or typical speeds?
We were told that during the challenge, the maximum speed would be 30 miles an hour. So that two vehicles coming at each other at 60-mile-an-hour closing speed. It's actually pretty significant. All of the software and the sensors were designed to react to a safe operating speed of 30 miles per hour.
Okay, but on the side, how fast have you guys taken this just for fun, or for your own testing?
I can neither confirm nor deny.
Pretty fast, huh?
No, actually, we've pretty much just done 30 miles an hour.
Okay.
We've had no reason to take it higher than that.
Sure.
Yet.
After it's lived its purpose, maybe you'll have a little fun with it then.
Hopefully.
Why'd you go with such an enormous vehicle? Is this full to the roof with electronics in there?
Well, it's actually a very versatile vehicle. It has a fantastic turning radius. It has all the space that we would need inside. What we do is we keep a lot of times 4 people inside of this. For development work, we've installed a small table in between with little cup holders and outlets and Ethernet access back to the computers. But it's comfortable for the developers. They actually spend a lot of time in the vehicle with their laptops or software, and they can get an actual feel for how the software is affecting the final product.
Does each of those guys have a big red panic button in front of them to stop if there's something bad happening?
There are several panic buttons around the vehicle, and we've got 4 mounted on the roof and 1 inside.
Okay. Can you tell me briefly which each of these subsystems are and what they do without getting too super detailed?
Sure. We've got 3 GPS antennas mounted on top, and we use 3 without getting into too much detail so that we can get a very good fix on where we're at, and we can also orient ourselves where we're at. In the back here, we've got a couple of close-range radars. These are MACOMs, and some long-range radar. And we've also got a planar LiDAR back here. It's a laser that shoots out in a plane. Up on top of the vehicle back here, we have it's called a Velodyne, and that will actually spin. And it's got 64 lasers in it that spins at 10 hertz and produces about 1 million bits of data a second. It's a very useful tool to have. Also up on the front, we have more radars and LiDARs, both short and long range. And on the sides here, we have the pan heads. You see the small units that are sticking down from the framework up there. When you come up to an intersection, typically you'll look left and look right to see when it's safe. These will actually pan out and search for where traffic would be coming from off of the roadways, and decide when be able to track the vehicles that are coming in and decide when it's safe to come out and merge into traffic.
I think those should be standard on California drivers.
That would be really nice.
It does even look at that.
Even just that alone, to let people know that they're about to pull out into an unsafe situation, would be a really nice thing.
That would be awesome. That'd be great. What else can you tell me? Give a dollar figure. How much you spent on this?
I don't.
It's a lot.
Yes, it is. The prize for winning the challenge was $2 million. We're very happy to receive that.
And that went somewhat towards
we're very happy to receive that.
Very good. Excellent. What's nice to know, Carnegie Mellon obviously is a huge robotics presence, huge robotics department. Will there be continuing vehicles next year? Each year students will build a new project? What's in the future?
We'll be obviously pursuing the technology in many different ways. We're in the process of working up different projects right now.
Okay. I understand that a lot of these DARPA challenge vehicles, now that DARPA has seen that these problems can be tackled, a lot of this technology is moving to the private sector to refine, to shrink these down, to fit them into the bumpers, make them invisible. So is that taking the fun away from the students who are going to do projects next year?
No, well, that part of it is not there anymore, which is true. DARPA's intent was to direct the technology to make it capable to have driverless vehicles. They're satisfied with the direction that the technology is headed right now. So we don't expect to see any more of this type of challenges coming out of DARPA. But what it has done is excited the community, generated an interest in vehicle safety, in autonomous driving, and all the benefits that can come from this technology, bringing it out into society. And every year, 42,000 people a year die in the U.S. in auto accidents. Pulling out some subsets of this technology and getting it out into the marketplace, we've been working with General Motors, and they're very excited about this, to be able to save lives and enhance the whole driving experience and make it safer.
Great. Now, you mentioned that a lot of these systems are modular here and not very integrated in the car. Can you unbolt all these items and put them on a different car and run that car autonomously?
And that's some of the projects that are out there also. Now that we know what the requirements are, what it takes to be able to travel at these speeds in the city, and what types of resolution and being able to track speeds, track vehicles at what speeds and distances. We have an idea of what's required now, so that the sensors can be developed for that purpose.
When you're going to run this vehicle on a certain course, how much knowledge of the course do you need beforehand to program into it, or can you just plop it down anywhere and it'll drive great anywhere?
It's a combination of both. We do need to be given or to create a route network. So we can do that through a satellite image, through what they call a geotiff that's available from the government on the web, or we can actually just drive it and record the waypoints and create the roadway that way. The more information we have, the better, but this machine is very versatile and very robust. It's capable of figuring out where the road is. Part of the challenge that DARPA had laid out was sparse waypoints, and what they did was they basically said, here's the beginning, and gave you a few points in between, and then they cut a dirt road down through over a hill, and you had to be able to figure out where the actual road existed and make your way down through.
Okay, so you were driving without prior knowledge in certain parts of the competition.
Exactly,
Very good.
Right.
Today, Are you going to let it drive itself to the track, or are you going to steer it manually to the track?
We'll take it manually to the track, and then we'll let it fly.
How fast will you go around this 2-mile course?
What our time will be, I don't know. We're running with the proven program that we have is 30 miles an hour. So each of these vehicles, that'll be the maximum speed they're allowed to hit.
Okay.
So we'll have to see how each one handles in the corners, I guess. But it's really not here as a competition. This is a chance to show the technology, show where we are with it, and to see about generating interest in the advancement.
That's great. It's very impressive. Anything I didn't ask you want to add that I missed?
This is a fantastic field to be in. It's very exciting. It's growing really fast, and keep an eye on it.
Great. Congratulations on your win. It's a nice looking vehicle, and good luck today.
Thank you very much.
Thank you.
Can you describe what we're looking at?
Real quick, what we've got here is you've got 10 blades of Intel's dual-core processors, some data logging equipment. We've got an Applanix up here that's takes input from GPS, inertial movement, and some encoders. It helps to figure out where we are sometimes when we lose GPS. We have this is a remote kill that's will be used. Well, actually, it'll be used to start the vehicle. What we'll do is we'll have the vehicle in pause. We'll put it in autonomous and leave it in pause, and then when they give us the command to go, the only communication that we'll have with this vehicle is go ahead and run. And then we'll also have the capability of pausing it if we think we need to. But that's typical with any robot, especially ones that run out under their own power and their own decisions.
Yeah, I recognize that one.
Because they blocked it.
When I first seen him, he was crouched up on the ground with the camera. Yeah. It's that It's starting by itself. It's driving itself. It's all by itself. It's got all the sensors. Joystick skills.